Think of a database like a giant filing cabinet. Inside that cabinet, PostgreSQL, one of the most popular database systems in the world, organizes all of your information into neat, identical little folders called pages. Each one holds exactly 8 kilobytes of data. To keep everything running smoothly, the system enforces a hard physical boundary. A single row of data, say a single user's profile, must fit entirely inside one of those 8 kilobyte folders. It is never allowed to spill over into a second folder. But modern apps don't always play by these neat, tidy rules. Sometimes a user uploads a massive 1 megabyte document or a huge block of text. We now have a giant payload slamming into a tiny metallic box. It simply does not fit into the space. PostgreSQL avoids a crash by handling the situation automatically in the background. It uses a specific mechanism to rearrange how that data is stored without the user ever seeing it. To comply with the 8 kilobyte limit, the system uses a storage workaround that reorganizes how data is saved. This behind-the-scenes workaround is called TOAST. That stands for the Oversized-Attribute storage technique. In a database, an attribute is just a fancy word for a single piece of data, like a specific field in a row. Anytime a single row of data grows larger than about 2 kilobytes, roughly a quarter of our total folder size, the TOAST manager steps in and intercepts the write request. Step 1 is compression. The system squeezes the data down as tightly as possible, attempting to shrink it enough to stay behind that dashed boundary line. If the payload is still too large even after being squeezed, the database moves to Plan B, storing the data outside of the main folder. Step 2 involves a physical change to the data. The database takes that dense, oversized payload and slices it up into uniform, bite-sized pieces. Each of these chunks is capped at around 2 kilobytes. Then it takes those slices and slides them over into a completely separate hidden storage area. The secondary container is what we call the toast table. By squishing the data and slicing it into manageable pieces, this pipeline tucks the massive payload away while respecting physical limits of the primary folders. Of course, the main row still needs a way to find all those slices when you ask for them later. So in place of the massive document, Postgres drops in a tiny 18-byte pointer. Think of this pointer like a coat check ticket or a package tracking number. Small, lightweight, and easy. This ticket contains a unique ID code and the exact coordinates of the hidden toast table. It tells the system exactly where your sliced-up data lives. By trading a heavy megabyte-sized document for an 18-byte ticket, the primary rows stay small. This leaves the main folder almost empty, allowing the database to pack hundreds of rows into a single 8-kilobyte page. This slicing and tracking architecture isn't just about saving space, it is designed for speed. When you search your database, the system scans through those primary folders. Because the heavy data is hidden away, the scanner glides right over those tiny tickets without stopping to load megabytes of text. Primary folders remain packed with rows, and memory buffers stay uncluttered, allowing for fast read operations. This is the secret to scanning millions of rows in seconds. By moving the bulkier data out of the way, the main table remains lean. But there is a catch. If you aren't careful with how you ask for your data, you can get hit by a performance penalty known as the toast tax. This happens when you tell the database to return every single piece of information in a row, a command commonly known as select all. If that specific row contains massive hidden documents, you essentially force the system to do a lot of extra work. The scanner has to screech to a halt. It reads the ticket, goes to the hidden toast container, retrieves every single slice in order, and then has to stitch them back together and decompress them just to show the result to you. To avoid this slowdown, explicitly ask for only the specific information you need. That lets the engine completely ignore the tracking tickets and skip the toast table entirely. Modifying even one letter inside a sliced-up document triggers a complete rewrite. The system generates a brand new tracking ticket and copies every single slice into a new location. All those old slices are left behind as dead weight, taking up space on your drive until a routine cleanup process clears them out. Slicing and pointing keeps Postgres efficient, even with massive datasets. Understanding these underlying mechanics allows you to harness the full potential of the database while avoiding these hidden performance traps.